Hello everyone. How are you all doing? Um, Today we have Codeforces Division 2 round number 769, which is actually testing, this system testing right now. It's 85% complete, yeah. So today I will be doing this round on stream. I can take a look at the problem names now and try to think about what the problem could be. But is the stream a fancy iPad stream? It probably is. Or maybe not. We'll see soon. Yeah. But it should be. Like previously with Codeforces Division 2 rounds, I will try to explain my solutions on the fly. I'll solve A and then explain A, I think. And then so on with B and C. Like try to explain the problem right after I solve it, or maybe even during. And yeah, my original intention was to do a virtual participation after system testing is over, but yeah, sometimes system testing takes more time. So maybe I won't actually wait for the end, but we'll see. Yeah, there's not much difference whether I do it or whether I start right now or after system testing, just because the difference is I can start virtual participation, but since I'm still not like competing, I'm not trying to win, I'm trying to solve the problems and explain them during the process instead. I guess my virtual participation doesn't matter too much, but we'll see. I'm gonna explain. Yeah, let's see. I'm trying to set it up right now, actually. Okay, 89%. Maybe we can wait. What exactly is system testing? So Codeforces round rules work like that. You submit a problem, and during the contest, it's not tested on the full set of tests. It's only tested on pre-tests, so-called. And you get the result of testing on pre-tests. And if you pass pre-tests, then your solutions are tested on full tests after the round, and that's what's called system testing. Yeah, I'm not sure about my iPad. I guess I'll just take a little bit of time to fix if it's broken. Why haven't I submitted problem F in round 768? Because I actually couldn't solve it. I spent a lot of time trying to come up with something, and I just couldn't. I don't know. It's a bit hard to explain maybe, but that's what actually happened. Like, I legit had no idea, even though a lot of people were solving it. But that's fine. Like, we have ups, we have downs. 4K not that day, but maybe someday in the future. Okay, let's see. Is it a fancy iPad stream? I guess it is. Hi chat. Is it a fancy iPad stream on the left? Yeah, it is. Okay. Alrighty. Why the old school IDE? Yeah, I'm just used to it. It's probably the most honest answer. And another thing is that just it's good at reacting, like you can do everything very quickly in it. But I'm down to try other IDs in the future. I'm just a bit lazy to set them up for the stream specifically or for like other contests. How is the stream software and game development? Yeah, I don't know, like we don't have competitive programming category at Twitch yet. Should it be like the other category is science and technology? Is it better? I'm not really sure. Yeah, this is probably the most relevant. I don't know. I do develop some, I don't know. I write some code. Probably that's it. Okay. So iPad is working. We have 94%. Let's take a look. Yeah. It's an esport. Yeah, I guess, but still there's no category for this specific. Like esports, some esports maybe, yeah. Okay. 95. Yeah. What else? Yeah, I saw someone asking for ABC, which is at Coder Beginner Contest. I actually like them. I think they're good for training and whatever. And I did some of the previous at Coder Beginner Contests as well, and I might do some of them on stream in the future. But yeah, today we had one, but I don't know. It ended like it ended right before Codeforces, right? So yeah, there was no time to do it before Codeforce. $96. Okay, I guess I'm already baited to wait, but like I'm not sure if that's a good idea. But whatever. Division 1 is the stronger division, and Division 2 is the, I don't know, weaker. I mean, for Division 1 has harder problems, and Division 2 has easier problems. That's all the difference. Yeah, yesterday's Code Chef contest was good. It only had 5 problems in Division 1, so you had to think a lot. It was for 3 hours, and 3 hours and 5 problems is actually quite a lot of time. And I started a bit slow, but then I managed to come back a little bit and solve the last problem before Maroon K, who was in the second place eventually. But yeah, it has some nice problems. Okay, 98. Oh. Good morning, second thread. How are you doing? Did you do this contest? Actually, I looked at the standings. I guess it doesn't matter too much. The solve counts look somewhat reasonable. Like the ratios are maybe a bit high somewhere, but it's okay. So I guess the difficulty gradient was fine. We'll see. We'll see pretty soon. It's currently 8 p.m. at where I am, which is Belarus. Yeah, you did. You did AD and didn't finish debugging E1. Okay, we'll try to do better. Okay, 99. Not really sure why I'm waiting, but I am. It's okay. It's okay, we'll cut it from the YouTube video and... Okay, I won't cut it anyway. Why do legendary grandmasters solve Division 3 contests? Maybe just to practice their typing speed or thinking speed as well. Like, you still have to think a bit about the last problems in Division 3 and like especially Division 2 as well. So yeah, I think that's it. Okay, 100% already done. Almost done, I mean, yeah. Finished. Practice. Okay, now we can start virtual contest. Nice. Let's go straight into it because you've already waited enough. 20, okay, 18. So 2018. Okay, 1 minute. Oh, stream appears finished at Codeforces. Thanks for telling me. It should not, but I guess something happened. Yeah, it's not finished. Thank you for letting me know. Actually, I don't know why, but it's okay. Okay, so we'll start with problem A. So we can go. Okay. Yeah, normal people. Yeah, I think that it's like typing text and typing code are different skills, right? All right, so problem A. The students of school 179 have developed a unique algorithm which takes a binary string S, and they soon found if some substring of S is a palindrome of length greater than 1, the algorithm will work incorrectly. Can they reorder the characters? All right. Let's see. Let's just submit first and then we'll discuss. This is obviously the easiest problem, but yeah, hopefully I got it correctly. Will it test quickly? Yeah, I guess. Accepted, yes. Good. So yeah, problem A, I don't know, like it's a bit, it uses a bit like well-known idea. I think it was used multiple times on my memory. Yeah, I can also turn on the timer, but it's late, so just whatever. Yeah, so the question is about palindromes of lengths greater than 1. And we want the string to have no substrings which are palindromes, right? So what does it mean? First of all, we have some string, I don't know, s0, s1, s2, sn minus 1. So we want to have no palindromes. No palindromes, I don't know, of lengths greater than 1. What does it mean? We want, first of all, no palindromes of lengths 2, right? So it means that s0 is not equal, should not be equal to s1 if we want the string to have no palindromes. S1 not equal to S2 and so on. And like in general, Si not equal to Si plus 1 because we don't want palindromes of length 2. And then what about palindromes of length 3? We don't want them either. So for example, yeah, this was for length 2, and now for length 3. Take the first 3 characters, it should not be a palindrome, so S1 is always equal to S1 to itself, but S0 should not be equal to S2, right? So S0 should not be equal to S2, and then similarly S1 should not be equal to S3 if we don't want any palindromes of length 3, and so on. And Si should not be equal to Si plus 2, right? So we actually have 2 conditions which should be satisfied if we want the string to have no palindromes of lengths greater than 1. And it turns out that these 2 conditions are actually sufficient. If these 2 conditions are true for any I, then it means our string has no palindromes. Otherwise, it does have some palindromes, right? Obviously. But any palindrome will have, like if a palindrome is of even length, the 2 middle characters will be equal, and we will get to this case. And if a palindrome is of odd length, then we will have 2 characters at distance 1 equal to each other. So we'll have this case. So yeah, what does it mean? In this particular case, we have binary strings of characters 0 and 1. So it means that what we want is actually what I already written here. We have S0 should not be equal to S1, S1 should not be equal to S2, and S0 should not be equal to S2. What does it mean? Like, if we have 3 characters that should be pairwise not equal, they cannot be just binary 0 and 1, right? So it just means that if length of S is at least 3, then it's always no. Just because in case of binary strings, the first 3 characters should all be distinct, but they can only be 0s and 1s. So if length of S is at least 3, then it's always no. And otherwise, if length is equal to 1, it's obviously yes. And if length is equal to 2, then it's, just check whether S0 is not equal to S1. If it's not equal, then it's yes, otherwise no. Yes, I will upload this to YouTube. Yeah, I explained quite a lot, but it's okay. Yeah, the code was like this. Just check what I wrote in the iPad. And yeah, so why this is sufficient for any length, once again, like I briefly said. If we have some even length palindrome in our string, let's say of length 6, then we always have 2 characters that are equal and next to each other. For example, like A, B, C, C, B, A, right? Because any palindrome of length, like in general, any palindrome of length X contains a palindrome of length x minus 2, right? Because we can just chop the leftmost and rightmost characters and we will get a palindrome. Like this palindrome of length 6 has a palindrome of length 4 inside it, BCCB. And then of length x minus 4, we can chop 2 characters from each side and so on. So eventually we get to 1 or 2. We can just chop the characters, and actually in this case we'll have 3 or 2, right? We can also say it like this. So we only need to consider palindromes of lengths 2 and 3. Okay, that was problem A. Let's go to problem B. So it took me 1.5 minutes to solve it, and then 6 more minutes to explain it. Yeah, that's fine. Let's go. Problem B. It was decided to build a roof over a football field and consecutive vertical pillars. Okay, some bitwise problem, I see. The heights should be a permutation of integers from 0 to n minus 1. The maximum value of the bitwise XOR of heights of all pairs. Of adjacent pillars. Okay, so we want to find the permutation of integers from 0 to n minus 1, which maximizes this value. Yeah, I feel like, okay, like a bit irrelevant, but I feel like the first paragraph is kind of irrelevant to this problem. Like, I don't generally complain a lot about problem statements. I don't really like this one just because I don't understand, like, this makes 0 sense. I think the legends are better when they have at least some point in them. But it's okay, like, it doesn't take too much of your attention, like, you can still figure out what the problem is. I just think it was unnecessary. Going to the problem. Yeah, okay, so we want to minimize the maximum value of XOR. And the question is, can we actually find some lower bound on the answer? Can we find, okay, I guess I should actually type first. Maybe I shouldn't, but it's okay. It's okay, I can just, oh, come on. I can just explain first. So, can you have some lower bound on the answer? So let's say, I know, n is equal to 6. We have some binary numbers from 0 to n minus 1, which are 0, 0, 0, 0, 0, 1. I'll just write them in binary. 1, 0, 0, and 1, 0, 1. Okay? So we want to permute these numbers, and we want to minimize the maximum XOR of adjacent numbers. And so, can we figure out what the answer has to be at least? And it should be at least 4 in this case. At least 1 in this bit. Why is it so? Basically because we have some numbers which have 0 in the highest bit, and then some numbers which have 1 in the highest bit. And we will have to have one of the numbers from the one group and a different number from the other group next to each other. Like, we will have to go from one group to the other group at some point. Like, no matter how we permute the numbers, if we just permute them, I don't know, like this, maybe if we just don't permute them at all, I don't know, like 1, 0, 0, 1, 0, 1. Like, you cannot permute them so that numbers from the same group, from different groups, never are adjacent. So it means that the answer is always at least 1, 0, 0. You cannot make it smaller. And now, how can you actually, like, can we actually make a permutation where the answer is equal to 100. And actually, yes, we can. And for example, in this case, I can see that it's easy. We can just have, like I said, we have two groups of numbers. We can have each group next to each other. We have one group and then the other group. And then all XORs of numbers in the same group, they will all be smaller than 100, right? Because numbers in the same group have the same highest bit. And the same, like numbers in the same group have XOR smaller than 100. And the only place where we can get XOR too big, for example, here we'll have XOR at least 100 between the groups, right? When we go from one group to the other. And so we only need to care about this XOR, this black XOR, and how do we minimize it? We just need to have two numbers which differ by exactly that amount, 100. And for example, we can just reverse the first sequence, or we just like we don't need to reverse, like we just need to put 0, 0, 0 and 1, 0, 0 next to each other to get the final permutation. And then here we just write all the other numbers with the highest bit set, and here we write all the other numbers with the highest bit unset in any order. We don't care. Yeah, like first group is highest bit 0 and second group is highest bit 1. So yeah, what can we do? Okay, let's type some code. We have some test cases. We have some n. So like I said, we want to find the highest bit. Let's do it like this. Oh no, by 1, or we can also write like this, it doesn't matter. And then I don't know, let's type p, and then okay, no line break. Okay, like this. Let's see. Okay. I'm pretty sure it should be right, but let's see. Okay, accept. So basically what I did in this problem, like I said, the order doesn't actually matter, the order inside the group, but I just reversed the first group and kept the second group as is. So like here you can see, the first group was numbers from 0 to 7. They don't have the third bit set, and 8 and 9 have the third bit set. So we just reverse the first group, and then we don't reverse the second group, and then just we get the smallest possible value, which is 8. Okay, there's some discussion in the chat, but I guess it's good enough if there are no real questions. How did I figure out the lower bound? I don't know, like kind of from experience, but in general, like it's not like something you cannot figure out. Like you want to see, like, I don't know. Yeah, I shouldn't answer this question. I don't know. How to make it logical? Like looking at the highest bit, looking at the small, like at the lowest bit, there are some different ideas then that you can apply. So in general, if you try different ideas, you can figure out which works and which doesn't. In this case, you should look at the highest bit, and you can see that since XOR, like the value of XOR depends on the highest bit more than anything else, right? So you want to minimize the value in the highest bit, and so that's kind of it. Okay. So Why do we need to reverse the part before 0? We don't need to actually reverse it, but what we need is, like, here is the place where one group meets the other. And what we want to have here is we want this XOR to be exactly equal to 1, 0, 0. That's the most important thing. And to do that, we just put 1, 0, 0 here. We put 0, 0, 0 here. And then we don't need to reverse. We can just put it in any order. I just reversed it because it was easier to code, but in general, it doesn't matter. You can shuffle this part in any order, and you can shuffle this part in any order. Or you could also take different numbers on the boundary of the groups. For example, you could also take 0, 0, 1 and 1, 0, 1. Put them on the boundary, and then you put 1, 0, 0 here, and here you put the numbers, I don't know, in any order, 0, 1, 0, 0, 0, 0, 0, 1, 1. And that works too. Like, the main condition is that this XOR should be equal to 1, 0, 0, and it should not be bigger, right? Yeah, and how do we know that if we exchange numbers into groups, we do not make the answer better? Because the answer has to be at least this value, because at least some pair of adjacent numbers will have different high bits. So the answer will always be at least 1, 0, 0, just because you cannot make it smaller. You cannot have all XORs have 0 in the highest bit. So we have the lower bound, and then we can reach this lower bound. That's kind of how math often works. Yeah, you can also swap 0 and the highest number. It doesn't matter. Yeah, no timer. I don't know. Let's see. Okay, 19 minutes. It's okay. Let's go to the next problem. And next problem, problem C. Increase A by 1, increase B by 1, and replace A with the bitwise OR of A and B. The minimum required number of operations to make A and B equal. Okay. Let's see. So what can we tell about the problem? I don't immediately see the solution, but we'll figure it out. So first of all, A is smaller than B. And after we apply any of these operations, we can only make the numbers equal, but we cannot make A greater than B, right? If they are not equal, if A is smaller than B, then after any of these operations, we cannot make A greater than B. So we always have A smaller than B. What else? Oh, no, that's actually not true. Yeah, that was stupid of me, right? A equal to A or B, it could be greater than B. Yeah, of course. Yeah. Yeah, it's actually a bit kind of vice versa, is it? Yeah. Yeah, it's different actually. Yeah. For example, if A is equal to, I don't know, 1 0 1 1 0 and B is equal to 1 1, I don't know, 0 0 here, and we have, let's say, 0 1 1 0. If we do A or B, it becomes equal to, I don't know, 1 1 1 1 1 0, right? So it becomes greater than B. Okay, so let's see. Actually, let's solve a different problem. Yeah, as someone mentioned, yeah, A or B is actually at least B, not the other way around. Yeah. Okay. So Actually, let's see. What if A is greater than B? What can we actually do? I claimed that in this case, answer is just equal to A minus B. Like A greater than B cannot be given to us as the input, but once it becomes so, the answer is actually equal to just A minus B, right? Because we want to make the numbers equal as fast as possible. So we just increase B by 1 to make it reach A. If we apply the first operation, then we only make the numbers farther from each other. And also if we apply the third operation, then it's even worse probably. Okay, the numbers are at most 10 to 6, so 1 million. So we can maybe have some linear solution, but we have... Okay, yeah, I should read this one, right? Yeah, I saw that we actually have 10,000 test cases with 1 million each, but actually we only have the sum of b is at most 1 million, so we can definitely afford the linear solution here and still be fast enough. Okay, that probably makes it easier. So we can probably brute force some number of operations. Like the idea is, like, why did I even talk about a greater than b? The idea that is that if we just do a assign a or b, in this case a becomes at least b. So once we apply the operation of the third type, from this moment we have a at least b. We always need exactly a minus b operations. That's the idea. So after we make the third operations, we don't have any freedom after that. If we want to be as quick as possible, we should just increase b by 1 until we get to the finish line. So one way, for example, if we want a quadratic solution, I think we probably we can make it linear, but one quadratic solution we can figure out is, okay, let's write it here. So O of, I don't know, b square, I don't know, not maybe b square solution, but anyway, we can just do for x from, okay, yeah, it's actually b square, for x from 0 to, we don't need more than b minus a operations, just because we can always make a and b equal in b minus a operations. So for x from 0 to b minus a, for y from 0 to b minus a, let's say we actually make a equals a plus 1 x times, like assume, and b equals to b plus 1 y times. Like the order doesn't matter here, right? So we can just apply this operation x times and this operation y times. And then let's say that after this, we apply the third type of operation. So we do this after that, and then we apply, yeah, b equals to b plus 1, I don't know, like a nu minus b nu times. Okay. Yeah, actually, I'm already taking probably too much time on this problem, but it's okay. I'm just thinking it through. So how many operations do we need? We need, okay, so we can make answer is equal to to the minimum. Let's go. No, not like this. Of answer. And how many operations do we need? We need x operations plus y operations plus one operation, and then plus how many operations? A plus x or b plus y minus b plus y, right? Okay, yeah, that's a bit messy. I don't really like it. And we can initialize the answer with b minus a. Okay, so that's one way we can solve it in, I don't know, quadratic time. And now, what else can we do? I don't know, actually, yeah, maybe I'm missing something simple. That could be the case. But I think that at least one idea that you can use here is that you actually don't want to try all values of x here. Like, let's say we have some a equal to, I don't know, 1, 0, 1, 1, 0, 1. So that's one case. And then we also like want to increase it. So we can increase it to 1, 0, 1, 1, 1, 0. Then we can increase it to 1, 0, 1, 1, 1, 1. But this case is never better than this case. Like, it doesn't make sense to increase it by 1 after this, because you don't gain anything by that. You only make the answer worse. You increase x in this case, and you also increase this number, right? Always. So we don't actually need to consider this case. We could increase it to 1, 1, 0, 0, 0, 0. And that could be useful. And then again, 1, 1, 0, 0, 1, 0, 1. It's not useful because you just make a new 1 in the number. And then so on. And actually, like, yeah, you can so on. 1, 1, 1, 1, 1, 1 is never useful. And then 1, 0, 0, 0, 0, 0, 0 could be useful, and so on. So I think we can only check some kind of useful numbers of increases to a. Let's try to code it and then see what happens and what the easier approaches are. Okay, like I said, yeah, I should hide my iPad. Yeah, this actually, maybe there's an easier approach. Is there? Should I increment? Okay, so I was talking about incrementing a, right? That's like, yeah, that could be useful. I don't know. It could be useful to increase b, I think. I should also check, maybe, yeah, for example, we can check the example test cases. So in case of 2, 5, you want to increase 5 by 1 and then apply the third operation. But if you don't increase 5 by 1, then you actually get slower. Yeah. So I think you should increase b sometimes. Okay. Let's maybe put my iPad here. So okay. I will initialize like this. And then here I will just actually type the same thing I just did. I just wrote on my iPad x plus y plus 1 plus a plus x or b plus y minus b plus y. And then, yeah, I guess how to go to the next useful number, I should actually just add the lowest bit of a. What is the lowest bit of a? What is the easiest way to find it? New a is equal to new a or new a minus 1 plus 1, I think. And print the answer. One, 3, 2, okay. Let's submit and then we'll see. All right, accepted. So, is that the solution? Is there any better approach? This is n log n, right? Because when we add the lowest bit, like, yeah, we add the lowest bit. This is kind of the formula from the Fenwick tree, yeah, from the binary index tree. How to add the lowest bit to number. This is kind of like, you don't need to know this formula. You can just loop over the bit and then you add it, like, or you can do whatever. Like in this case, it doesn't matter. This formula is just the shortcut. Like you don't really need to know it or understand it to like solve the problem. Okay, there are just 4 ways to change a to b. This can be done in O of n. Just 4 ways to change a to b. Why is that so? I guess we can figure out why some ways are better than other ways. How to do that? Actually, 2 ways only? What 4 ways? Yeah, what 2 ways as well? I kind of wonder. In optimal solution, y is equal to 0 or x is equal to 0, you think? Why is that so? Only increase a or only increase b? That's what many people are suggesting. If we increase both numbers, what happens? I don't know what happens. Like, what happens to a plus x or b plus y? I'm not 100% sure. Why? Can we brute force all I or b equal to b and get minimum of a or a minus I? I don't quite understand. Yeah, okay. Okay, I'll just explain this formula. Add lowest bit to new a. to x. Let's say x is equal to 1, 0, 1, 1, 0, 1, 1, 0, 0, 0. I want to add the lowest bit to x. If I add the lowest bit, I get to 1, 0, 1, 0, 1, 1. Okay. 0, 1, 0, 0, 0, 0. So like this is the next useful number. Because like I don't want to, like it makes some other bit different. Like I don't know how to explain it the best way. And yeah, so the formula is just take x minus 1, which is equal in this case to this. Then you take x or x minus 1, which is equal to this, and then you add 1. But yeah, it doesn't matter. Like again, you can do other, you can use other methods. Whatever. Let's see at the, can I show the second test? Sure. What is the second test? You mean the second test? Not the second test case, but the second test? I don't know. Okay. Yeah, interesting. I don't know. I guess I will check some proofs later, because you can check all the proofs in Codeforces comments yourself. I guess I'll check them for myself later. I assume there are different approaches you can take, and I don't know, maybe you can guess your solution. In this case, I didn't actually guess a lot. Like I think I understand pretty clearly why my solution is correct, but it's n log n. Maybe there is some linear time solution which are more or less tricky to prove. I don't know. Like, yeah. Yeah, I mean, you can come up with a lot of approaches, and then you might get lucky if you don't really understand what you're doing, but you made some formula which works, and then it passes the examples and then passes the whole problem. Good for you. Like, you can also try some brute force solution and then figure out the formula yourself. Like maybe you can stress test it against some slow solutions, like the quadratic solution I provided, and then maybe some BFS, doesn't matter. And then you can try it this way, and then like you can prove it by stress testing. That's also a way. So you need to get accepted, so it doesn't really matter in general which way you take. But again, in general, you would actually want to understand your solutions, to like have some, maybe not even strict proofs, you don't need them, but at least some intuition why this or that would work. Because I have some solutions in the chat, like I don't understand them clearly, I don't see immediately why they work or don't, but if you can figure out why your solution works, then it's good enough for you. Like I have my way of solving it, which I understood, but sure, like there are multiple ways, and also like be sure to explore other ways. I will do that after the contest for sure. So seeing how other people approach the same problem is important too. Okay, let's see. I think let's move on to problem D actually. It was enough of problem C. I guess problem C was the most painful problem for most people in this contest. But I showed at least some way to try it. Like always, I will upload this stream recording to YouTube after, in a couple of days, so just check it after that if there's anything unclear, or you can also watch the video on Twitch as well. Even of this stream, you can rewind it right now if you feel like that. Okay, what is problem D? We have n classes in the school, numbered from 1 to n. The I class prepared of a scene of length AI minutes. Okay. If we have some subsegment of length at most, well, no, of any length, such that the greatest common divisor of the numbers of this subsegment is equal to its length, then the audience will get bored. Okay, that's again like some really cool story. And we can ask any number of times to change a number, and we want to make the smallest number of changes to make the array like good. And we want to know the answer for every prefix. Okay. Yeah, I think this problem is probably easy, but what can we do? Okay, so first of all, I think that we can just find all segments in the initial array that are boring, that have GCD equal to length. We can just find all such segments, right? Can we? Yeah, we just can. Okay, let me code first in this case, and then we'll discuss. Is the stream okay? Can you hear me? Yeah, I think you can. You can hear me. Okay. So okay, I guess there are multiple ways to actually do it. Answer is equal to 0. Yeah. Okay, I'll figure it out. So, okay, let's say I have a race of 3 of all segments. And now okay, I don't need another array. Okay, from I to I, it's equal to AI. Okay. I guess I can do it in the other order, doesn't matter here. And now I want to merge some segments. Okay, and now okay, and now um, Okay, it should be this position. If it is inside, then I think something like this. Let's see. Okay, let's submit. Accepted. Okay. Good enough. So, this problem is, yeah, it has a couple of steps in it. But yeah, my code is probably the easiest you can have in terms of the amount. I guess that you can use some binary search and segment trees and stuff, but you don't have to. I'll check the bot later, yeah. Sorry about that. You use two stacks to make a queue where you can ask for GCD of the whole queue. Then the problem becomes easy. Yeah, there are multiple ways to deal with GCD, but okay, in general, so the idea is that first of all, we want to find all segments which are actually like boring. And we can actually find all of them. And it turns out that there are at most n times log of the greatest number such segments, which I'll explain a bit later. And you can just find them, and then after you find them, it becomes a problem like what? Is it actually like, yeah, I actually didn't think about my solution. Like you can change some number into any into any integer. But my assumption in general was that I can, like, I have an array, I find all boring segments in this array. They could be like, I don't know, like any type. And then I thought that the problem is kind of like you have to change some elements. You can, I was assuming I just remove some elements so that each segment gets at least one element removed on it. I guess, yeah, I guess it's okay. You can, is it okay? Okay, let's think. Yeah, okay, I can just change the number to any positive integer. I can change it to any big prime number, which is like not in this array yet. And then all segments of length 1 will have this number, which is not equal to 1. And all segments of length greater than 1 will have GCD equal to 1 because of this prime. And 1 is not equal to the length. So yeah, it works, but I didn't really think about it during solving it. But you think there are even a linear number of bad segments for every right end, there is only one. Oh, yeah, actually even a linear number. Yeah, I see. Actually even a linear number. But okay, you don't really need this observation. But okay, so when we find all such segments, the question is just how many points. We have a line and we have some segments on the line. And the question is how many points do we need to choose so that each segment contains at least one line. And the solution to this subproblem is kind of like well known, I would say, like it's greedy. The idea is that you sort all segments in increasing order of their right end. So you take the first segment and you check whether this segment contains any points. If it doesn't contain any point, then you take it right bound and you put a point here. Okay, so And then you don't need to actually check all the previous points. You only need to check the last point, whether your next segment contains the last point you put. So then you take the next segment with the smallest right bound. It contains the given point, so you don't need anything. Then you take the next segment. It contains the given point, like the last point you put, so you don't need anything. And then take the next segment. It doesn't contain the last point, so you put another point at the end of this segment. And the reason about the end of this segment, like not the beginning, not the middle, is that you took the segment which ends in the leftmost possible point. So any other segment ends to the right of this point. So if you move the point you choose to the left, you don't achieve anything. You don't allow any new segments. That's the idea. So you can always put it to the right point. So that's kind of the greedy idea in general for the problem about segments on a number line. And then how do we find all such segments? Let's go from left to right. Okay, for example, maybe we can check the exam, like the actual problem example. Can be. Yeah, let's just try this array of numbers. So we have 2, 12, 4, 8, 18, 3, and 6. So you go from left to right, and for each prefix of the array, you want to find all different GCDs, all different greatest common divisors on the suffixes of this array. So for example, you take 2, and here you can only have GCD equal to 2, right? You take 12, and here you have two options. If you have a segment of length 1, its GCD is equal to 12. If you take a segment of length 2, its GCD is equal to 2. So then you take 4. What do you have? You can have length 1, GCD will be equal to 4. You can have length 2, and GCD will be equal to 4 as well. And you can then take length 3, and then you have GCD equal to 2. So the idea is that you, okay, let me just do it like this. The idea is that you maintain all segments where, like all segments of left positions where GCD is equal for a fixed right position. So for example, in this case, when we are at 4, we have one segment from position Z. Okay, so positions are numbered 0, 1, 2, 3, 4, 5, 6. So from position 0, like let's say the right bound, I equal to 2. So first from position 0 to position 0, if the left bound is from 0 to 0, then GCD is equal to 2. So like from 0 to 2, because we just have GCD equal to 2. And then if the left bound is from 1 to 2, then GCD is equal to not 2, but 4 in this case. So you maintain such tuples of 3 elements. You can probably have pairs, but it doesn't matter. And you just, like each tuple is from, to, and value. And it means that for any subsegment such that left is from to right, from to 2, and right bound is equal to I, GCD is equal to V. So you just maintain all such tuples. And then when you go to I plus 1, it's actually easy to change these tuples, because you just, so what happens, you take all the tuples, and each tuple you change the value to GCD of that value and this value, and you put a new tuple, which is for the one element segment, you just put a tuple for a segment of length 1, yeah. And then you can also merge segments which correspond to the same value. You take pairs of neighboring elements which have the same value, you can just merge them. So I just like merge them here. And I remove, like, decrease number of tuples this way. And then the main idea is, why is it fast enough? Like, why is it better than just checking all possible subsegments, which you have n square of them, right? But why is it better? It's better because GCD is actually decreasing quickly enough. So in general, like, yeah, you can probably find this idea and this technique in multiple sources. I don't know, multiple problems probably, right? I don't know about sources because, like, it's not some standard algorithm, but it's kind of an idea which appears from time to time in problems. Let's say you have some GCD here, okay, G0, you have some GCD here, G1, you have some GCD here, G2, and so on. You have some GCD here, G and -1, I don't know. So you have GCDs of all suffixes of some array, let's say. So first, what do you know? You know that G0 is greater than or equal to G1, right? Because when you include a new element, the greatest common divisor can only decrease. Greater than or equal to G2, and so on. Greater than or equal to Gn -1. And then another thing that turns out is that Gi is always equal to Gi plus 1, or Gi is at least twice Gi plus 1. So just because obviously Gi is actually divisible by Gi plus 1, right? So since we know that, just because it's like some divisor of, we ended a new number, so GCD can only be a divisor of the old GCD. So since we know this happens, it's like the result of division is either just 1, in which case the numbers are equal, or it's 2 or more, so in which case we have this case. And so what follows from this is that the number of distinct values among G0, G1, Gn -1 is at most log of G, okay, O of log of G0. So it's actually binary logarithm, but it doesn't matter. Because every new number should be at least twice smaller than the previous number, right? So yeah, GCD changes at most not log n times, but log biggest number times, right? So biggest number is at most 10, okay, 1 billion in this problem, right? So it changes at most 30 times. Yeah, can you please use English in the chat? Thank you. In placeback is, yeah, you can check it on Google, but it's similar to pushback, but it's a bit different. Okay. Okay. I don't know. That was problem D. I hope someone found this explanation useful. Let's go to E. Okay, a tree is a connected, how many? Okay, we have 1 hour, it's okay. A tree is a connected undirected graph without cycles. Yeah, I guess. A weighted tree has a weight. Distance is the minimum sum of weights. Okay. We have a weighted tree with n vertices. Each edge has a weight 1. Oh, hi Lydia. Some people are using different languages. Can you please, I don't know, explain something to them? Thank you. Okay. Minimum possible value of maximum of dv. If I can add an edge between any two vertices, A and B. Okay. So we have 3000 in the easy version and 300,000 in this hard one. Yeah, okay. Yeah. Want to minimize the maximum distance. Oh, each edge has a weight of 1. Oh, and we want to find f of x, and x is the weight of an edge we are adding. Okay. Okay. So one idea is that probably we only need to add edges from the root. I guess it doesn't make sense to add edges between two vertices, which are not roots. Like the root is vertex 1, and I think we should always add an edge between the root and something else. Right? Right. Probably right. And then what else? So we can just do binary search on the answer, but I don't see how to... Also, yeah, we also have to solve it for each x, so yeah, it's not really viable to do something for each x separately, unless we're solving the easy version. But yeah, I'm not like trying to solve specifically easy version or hard version, because they don't really differ. I'm just currently trying to have some observations about the problem, which will help me with like in both cases. But mostly E2. Like yeah, I'm probably going for E2, but it seems that I might have some slower idea at first. In any case, it probably will be true. So I have some edge of length x. Like yeah, like one cubic solution and cube solution could be for each x, try which vertex we add the edge to from the root. I think it should be right that we add it from the root. Yeah. And then just find the shortest path in linear time, which will be n cube. I did not leave the last problem of the last division 1 round on purpose. I just couldn't solve it. That was it. I was definitely trying to achieve 4K, but out of luck that day. But like, it doesn't really matter. Like, it's not like I reached 4K and then stopped competing, right? So just whatever. A rating is just a number, as wise people say. What about this problem? I really, like, yeah, I don't really understand something about it. Hmm. It's just a number once you're legendary grandmaster, but before that it's also a color. Yeah. Yeah, that's a good point. And a different color for different people. That's true. So one thing I was considering this problem. So we have some tree. Yeah, I guess this specific tree is not really interesting, but okay. Let's say like this. So let's say we want, like, we can solve a reverse problem as well. For example, we have some maximum distance and we want to find the smallest x we need to obtain that distance. Okay? Yeah, so let's say we have some distance. For example, let's say we have distance equal to 3. Like, this is the maximum allowed distance we can have. I don't know, this test case is just garbage, but whatever. What's the idea? Like, first of all, so this is the boundary of distance 3 vertices and greater distance vertices. Like, all these vertices have distance at most 3. And all these vertices have distance greater than 3. So what does it mean in general for us? We want to make the distance to the bottom vertices smaller than what it is right now. So right now it's more than 3, but we want to make it at most 3. Okay? Okay. So we check, like, we choose some vertex and we add a new edge of weight x. And we actually want to, like, and then, like, we add the new vertex with, like, a new edge with weight x. And then if we use this edge in our shortest path, then we have distance x plus 1 here. We have distance x plus 2 here. We have x plus 3, x plus 3, x plus 1, x plus 2. And what we care about is that the smallest, like the largest of these numbers in the bottom part should be as small as possible, right? So in this case, we want x plus 3. Well, not as small as possible, but not greater than d, right? Which is equal to 3. So in this case, we need x at most 0, which is not allowed, but that's like just the point. Okay, sorry, 1 second. Yeah. So yeah, it doesn't matter like specifically which D it is, but for some D, we have some set of vertices in the bottom part, and we want to find the vertex in the tree such that the biggest distance to some of these vertices is as small as possible. Like, for example, this vertex is good, like distance is 3, is the smallest we can get. Why is that so? Actually, we want to find the diameter of like the part of the tree on this vertex. We want to find actually two farthest vertices in this part. In this case, we want to find this one, let's say, and this one. So the distance between them is, so green distance is equal to 5. And so it follows that the diameter is 5/2 rounded up. Right? We can just choose the middle of this path, this vertex of this vertex. And it will be equal to 3. So that's the value we actually want to minimize. So what follows is that we can just increase, let's say decrease distance. We have some set of vertices. We add a new vertex each time. And we want to maintain like the diameter of this subset of vertices. Can we do that? Okay. It's easy to do in n square. Obviously, like just do the way I said it, but can we make it faster? So, for example, we can say it like this. We have some set of vertices and we want to add a new vertex. Well, yeah, I guess we can. Let's type some code. I guess I'll just type it for the second version immediately. But I guess the idea is that we can just maintain all the distance, maintain the current diameter. And then there's some property of diameter that is that any new vertex, if we want to find the farthest from one vertex to a set of vertices, we only need to check the ends of the diameter. Because, for example, when you want to find a diameter of some... Okay, yeah, I have to hide my iPad. Right. So when I want to find the diameter of some tree, there is a well-known algorithm, which is like not easy to prove actually. You take any vertex, you find the farthest vertex from this vertex. That's one end of the diameter, and then you take the like farthest vertex from that vertex, and then you get the second end of the diameter this way. So I guess we can just apply something similar here. First we need to find distances. Okay, let's just use some BFS, I don't know. Distance to 0 is 0. If distance is not set, then we put the vertex to the queue and we set the distance. Okay, now what do? We want to sort actually all the vertices by their distances, which is basically the same as just like, yeah, the queue is already the set of vertices sorted by distance. So we can just use the queue. Let's maintain the diameter from x to y, let's say. And initially it will be just consist of the last vertex in the queue. And then we have some vertex and we want to add it. And now we will need to find distances between any two vertices. And for that, we will need some least common ancestor. Let's just type it. I would usually copy some code, but I think we can just, I don't know, type it here because it's not too hard. So we save the parent of each vertex. Okay, pv parent. Let's be concise. And now, okay, we can just use some constant. Jump and log jump from I to 0 is equal to just, oh, what's that? Parent of I. And this is the standard binary lifting. Why do I need distance, the distance between any two vertices? We'll see now. So I think I need it because I want to recalculate the diameter. So I want to find the distance from Z to X and Y to actually know if I want to replace something. I think, yeah, I will need that. Okay, let's say get distance. Yeah. Okay, this is 0. Get distance from X to Z. Get distance from Y to Z. If the XZ is greater than D. Okay, let's say if I have a new diameter, then if the XZ is greater, then I should, XZ is my new diameter. So it means that I replace Y with Z. Otherwise I replace X with Z, and I also set D to DXZ and D to DYZ. Okay, I think that's it. Okay, how to calculate distance? Just find LCA, distance of U plus distance of V minus twice distance of LCA UV. How do I find the LCA? Okay. Let's make U deeper than V. Now we want to level U to the same level as V. Like, there are multiple ways to actually use, like, to find the least common ancestor. That's one way. If distance of U minus J is at least distance of V, we want to jump from U to 2 times by 2 times 2 to the power of J. And now, once again, I want to jump if we jump to different vertices, and then okay, if they're equal, I just return one of them, and here I return parent of U or V. It should not matter here. And so finally, I know the new diameter. So weight of the edge I add plus, okay, actually I know, yeah, I know the diameter. Yeah, I don't know, like here when I wrote diameter is equal to 5, like, yeah, it's not the diameter here actually. This is not diameter, this is kind of like radius, I think, right? And this is actually diameter. I think that's it. But yeah. So radius is equal to diameter plus 1 over 2. Weight plus radius should not... Okay, what is the bound on the distance if we only use those vertices? It means that we want the answer to be at most distance of q b minus 1. Yeah, we want this, so... Okay, and what does it mean? Here, let's just print something. For this bound, we have some weight. And let's see what actually happens on the example if we compile. Yeah, we actually do compile. We can add an int here, doesn't hurt. 1, 1, 1, 1 minus 1, 0 minus 2. Does it mean anything? Yeah, I think it does mean something. Yeah, it's probably correct. Okay. So, how do we actually find the answers? We want to find the inverse answers. Now, for each distance, we found the smallest weight. But in the problem, we need to find the minimum distance for each weight. Let's have some n+1 sized result. The answer is at most the initial maximum distance, which is the distance to the end of the queue, right? And here, if weight is positive, I want to say that the result of for this weight can be made at most bound, right? Right. And now, what do we have in the output? Okay, and now I think we just need to propagate the answers, because if you have some answer for some x, you can have the same answer for all smaller x. Okay. And then we just print. Okay. I don't know. Let's see. I guess it should work on the example. Yeah, let's submit. Okay, let's submit E2 immediately. Yeah, I guess we can submit E1 as well. All right. Solve this one. Yeah, this was a good problem. It's definitely my favorite one in this contest. It's kind of cool. What about, like, yeah, what about other solutions? I'm not really sure. My solution is not too complicated, but yeah, it uses some ideas of like maintaining the diameter. It's not like an easy idea. I can, like, yeah, it can appear in pretty hard problems in Division 1 easily. Like, now it's the hardest problem of Division 2. Maybe there are other approaches just because it's Division 2, but maybe not. Don't we need DP to find all pairs longest path? Probably not. Okay. So yeah, I guess a short recap of the solution. So, Yeah. First of all, the first idea is that we should always add an edge from the root. You can like easily see that if you have some different edge, you can change one of the ends to the root, and then you will be just better. Like left as an exercise. Then in the problem, we are asked to find the minimum possible value of maximum distance for each edge weight. But let's solve the kind of inverse problem. For each maximum distance, let's find the smallest edge weight we need to add. Okay? That's like a bit of a different problem, but if we know the answer to this problem, we can just inverse the output kind of and get the answer to this problem. And then for some value of d, let's say, okay, d equal to 3 in this example, we need to add some edge to make all distances at most 3. Okay? At most d in this case. So, as I said, like all vertices which already have distance at most 3 are fine. We don't need to touch them, right? We don't need to. We cannot make distance even better. Like we can make distance even better for them, but we don't need to because they're good as well. Already good, right? And then all the other vertices which have distance greater than d right now, we need to do something with them. If we don't use the new edge of weight x for them, then we just lost, right? Because we didn't make the distance to them smaller, but we had to do it. So for all of these vertices, which belong to the bottom of this black line, to the part below of this black line, we need to use the new edge to get to those vertices, to these 4 vertices in this case, okay? And now the question is like, where do we want to add this edge so that all distances become at most 3? And remember that we want to minimize the weight of this edge, right? So basically we have a lot of options. We can make the edge end in any vertex, and you can choose any weight, but we want to minimize the weight and make all the distances good. So since we have some set of vertices and we want to find some magic vertex, which is this one in this case, for example, where we will direct our edge so that the maximum distance from this vertex to any blue vertex is as small as possible. Why is that so? Just because we will have distance x leading to this new vertex, this magic vertex, and like any other vertex will have distance x plus the distance from this new vertex, let's call it v, to each of these vertices, right? So we want to minimize the maximum distance from this like magic vertex to the vertices in our set. I mean, yeah, minimize x, of course, minimize x. So what do? We want to find like kind of the radius of the set of blue vertices. And it turns out that the radius is equal to half of the diameter, which is kind of obvious when you talk about circles, but not so obvious when you talk about trees, but it's true as well. So we actually don't need to find this vertex which minimizes the distance from it. We can just find 2 vertices so that the distance between them is maximized. For example, we can take these 2 vertices so that the distance between them is 5, and then it will just mean automatically that the radius is half of that, rounded up, which is 3. And we can take either one of this, like either this vertex or this vertex, and both of them will give radius 3. Like in the middle of the diameter, we can choose any vertex if there are 2. And so what is left is that we just want to find the diameter of the set of all vertices below some line. Okay, and then how do we do that for all values of d at the same time? We can just take this black line, put it below all vertices, and then just try to move it up. So we move it up, we have just one vertex in the set. Okay, the diameter is equal to 0, so it's fine. Then we go up, we put the black line here, we add some U3 vertices to the set. Again, like decrease d, and when we decrease d, we add some U vertices to the set, and we want to recalculate the diameter quickly. And so on. We move up to the root. And then how do we recalculate the diameter quickly? As I mentioned already, so we have some set of vertices, and let's say you have some diameter, which is like, in this set of vertices, this is the diameter. And then you have some U vertex added to the set. And it turns out that the diameter is one of three things. One thing is just the old diameter. The other thing is the distance from one end of that diameter to our vertex, the new vertex. And the third one is the distance from the other end of the diameter to our new vertex. So you only need to check one of these three distances. Only one of these three distances will be the new diameter. So I maintain the old diameter, which is from x to y, from vertex x to vertex y, and the distance between them. And when I have a new vertex, I just check the two new distances and just change the diameter if it actually changes, and so on. And then, like, after I do that, I know the diameter is equal to d, I know that the radius is equal to half of d, I know the maximum weight I can choose. Actually, yeah, actually I want to maximize x. Yeah, I actually kind of said I want to minimize x. Actually, I want to maximize x. Like, in the problem, I wanted to minimize distance for each x. If I want to solve like the inverse problem, which is kind of the dual problem, actually for each distance, I want to maximize x, right? So I want to make the edge as big as possible so that I can still fulfill my goal. So yeah, I actually choose the biggest possible weight so that the condition is satisfied, and just update the answer. Yeah. Thank you. I drank some water, and now I'm out of water. But I'm also out of problems, so that's fine. Okay, that was it for today's contest. I hope you found my explanations useful. Actually, the problems were tricky, some of them at least. And overall, I enjoyed the contest, so thanks to the authors. We took, 10th place. That's decent, right? Last time, I think it was 12th or something like that. So we are definitely improving in our problem solving and explaining them on the go. I will post this video on YouTube as usual in a couple of days. So you can check it there after a couple of days. You can check it on Twitch. If you go to the videos part of my channel, you can watch this stream and some of the previous streams. Tomorrow we have the last round of Snark News Winter Series, and there's also educational round, but I don't know, maybe I'll do a stream of both, but it might, like, I'm definitely streaming Snark News Winter Series round 5, which is the last one, and that happens, I don't know, I'll post a notification. Codeforces, it's 22:30, like 10:30 p.m. Codeforces time, if you wish. And what else? Yeah, maybe I will stream earlier to also stream Codeforces educational round, which happens tomorrow, but maybe not. Probably not. We'll see. Check the Codeforces notifications, like not the notifications, but the Codeforces streams panel here. Check it here. Check it on Twitch. Like, Follow my channel on Twitch for instant notifications of future streams. What else? Yeah, I'm not doing another contest today, but anyway, thanks for the suggestion. What else? Yeah, I don't have any screencasts of previous contests, so there's not much I can do about it. Yeah, I'll try to fit some ABCs in the future. Educational, I think it's kind of the same difficulty as the usual Division 2. Maybe a bit harder in the hardest problems, but not that much of a difference. Oh, okay. Yeah, it's kind of funny. My internet actually broke right as I was going to end the stream. That's a good sign. I should end it here. See you all once again, and bye. Take care.